Welcome back to the Deep Dive. We are tackling a question that has been, well, central to human curiosity since we first really turned our gaze skyward. Is there, or maybe was there, life on Mars?
We're kind of taking that classic query, the famous line from Russia, and updating it for today.
Exactly. Is there life on Mars, or is there no life on Mars? Science is still figuring it out. And today we're going to try and figure out what science has figured out.
We are definitely moving past the romance and the speculation. We've synthesized a really comprehensive stack of foundational scientific sources data that spans decades of telescopic observation and goes right up to those critical and often surprising results from the first space probes in the 60s and 70s.
That's right. Our mission today is, I think, pretty ambitious. We want to unify this foundational knowledge, all of it, from the bizarre composition of the Martian atmosphere through all the geological clues that suggest a really radically different past, and then culminating in those famous direct search experiments.
The goal here is to understand what Mars actually presents, separating the scientific reality from what we've all, for centuries, kind of hoped for.
And to set the stage, Mars has long been considered the, quote, most prospective planet in our solar system for life.
And for good reason. Its proximity, its rotation period, it all sort of pointed in that direction.
But the reality that was revealed by modern spectroscopy and the first flyby missions, it delivered a series of incredibly harsh truths.
That's what we're going to explore. We'll unpack those realities, but at the same time, we'll look at the compelling evidence that Mars, way back in its history, was a dramatically different and, potentially habitable world.
So where do we start?
Let's start with the air, or maybe the distinct lack of it.
Before we can even begin to discuss the possibilities of life, we have to talk about the physical constraints. What was the defining scientific shock when researchers first got a proper look at the composition of Mars's air?
Well, the defining shock was really twofold. It was the composition and it was the density. First, the main ingredient, carbon dioxide, CO2.
Okay.
Spectroscopic analysis confirmed that CO2 makes up about 95% of the entire atmosphere.
95%. Here on Earth, we think of CO2 as this, trace gas that's driving climate change. But on Mars, it's pretty much all there is.
It is almost purely CO2. But here's the massive paradox. Even though the absolute amount of CO2 is about 30 times higher than what's in Earth's atmosphere.
30 times more.
30 times, yes. But the overall Martian atmosphere is incredibly, incredibly rarefied. It's roughly 150 times less dense than the air you're breathing right now at sea level.
So Mars is wrapped in this CO2 shell, but that shell is basically a near vacuum.
That's the perfect way to put it, a CO2 vacuum.
So if CO2 is 95%, what makes up that other, vital 5%?
Yeah.
On Earth, that margin is everything. It's our oxygen, it's most of our nitrogen.
On Mars, the remaining gases are primarily argon and nitrogen. And we should actually pause on argon for a moment.
Why argon?
Specifically argon-40. This isotope is really significant because it's the product of the radioactive decay of potassium-40 deep inside the planet.
So it's a clue about what's happening underground.
It's a huge clue. Finding argon-40 in these amounts is really strong evidence that Mars has gone through geological differentiation, that it has a crust, a mantle, a core, that it's experienced internal geological activity.
So finding argon-40 confirms Mars isn't just some dead rock. It's a planet that went through similar formation processes to Earth, making it a genuine planetary relative.
Precisely. And because oxygen is so incredibly scarce, there's almost no free oxygen in the atmosphere, these inert gases, argon and nitrogen, they become major, though still, meager components of the overall atmospheric makeup.
Okay, let's talk about water vapor. Given how bone dry the environment seems now, how hard was it for early astronomers to even confirm it was there at all?
Oh, it was tremendously difficult. Getting a reliable confirmation, it really marks a specific turning point in the research.
So when did they finally nail it down?
Firm confidence only really arrived in 1963. This was led by the work of American scientists Spinrad, Munch, and Kaplan. They used highly sensitive spectroscopy, and with that, they were able to detect very, very weak water vapor bands in the Martian spectrum.
And I'm guessing very weak translates to an environment that is, for all intents and purposes, bone dry.
Exceptionally arid. When they quantified it, they found that H2O vapor makes up only about 1,000th of the already dominant CO2 content.
1,000?
Yes. To give you some context, if you could somehow collect all the water vapor in the entire Martian atmosphere and condense it, you'd get a layer less than 10 micrometers thick across the surface.
Wow.
Yeah.
That's a staggering level of dryness. We should probably quickly mention the other trace components, too.
Right. Besides the CO2 and the tiny bit of water, we also find carbon monoxide, CO, at about 0.06%, and critically, ozone, O3, at an incredibly low concentration of about 10 to the minus 3%.
And the scarcity of ozone is going to become a huge problem later on, isn't it?
It is. As we'll discuss, it forms one of the largest physical barriers to any kind of surface life today.
This whole discussion of scarcity brings us to what I think is a crucial scientific paradigm shift. The realization that Mars's atmospheric pressure has just been continuously declining, or at least our estimation of it has.
This is where it gets really fascinating, because the history here highlights just how difficult early space science was.
So what is the pressure today?
The total atmospheric pressure today is, on average, incredibly low, only about 5 millimeters of mercury, or millimO-Hg. That's about 0.006 of Earth's sea level pressure.
A tiny fraction.
But just decades before the first probes, the estimates were completely different, wildly different.
How far off were we?
Over a period of about 2 decades, leading up into the mid-70s, scientists documented a continuous decline in what they thought the pressure was. For example, back in the 1950s, researchers like de Vaucouleurs were using polarization measurements and, these complex models.
Based on the idea that Mars was generally Earth-like.
Right. And they proposed a pressure closer to 65 millimeters of mercury.
65. That's still thin, but that's high enough that liquid water could potentially exist, right?
Right.
And low elevations at warm temperatures.
Precisely. That pressure was just high enough to keep the dream of a more Earth-like Mars alive. But then, by the 1963 observations, new data had already pulled that estimate down to around 20 millimeter Hg.
And then the space probes came along.
And then the space probes confirmed the current, vacuum-like reality of 5 millimeter Hg.
That drop from 65 down to 5, that's a massive scientific turning point. Why was the initial estimate so high, and why did it fall so quickly once we actually got there?
Well, the initial high estimates often relied on telescopic observations, measuring how light was scattered or polarized by the atmosphere.
Which sounds tricky.
It's notoriously difficult to interpret, and it's highly dependent on what you assume the atmospheric composition and temperature profiles are. The probes, on the other hand, they carried miniaturized gauges. They measured the pressure directly as they descended.
So they got an undeniable hard number.
An undeniable number. And when that 5 millimeter Hg figure was confirmed, it instantly killed that romantic vision of a planet with a substantial atmosphere and, liquid water on the surface.
It just shattered the illusion. And to relate this back to you, the listener, 5 millimeter Hg is a pressure that's only reached on Earth at an altitude of 30 kilometers above sea level.
Yeah. Imagine trying to live permanently at the upper limits of our own stratosphere.
That really gives you a tangible sense of the near-vacuum conditions any life would have to survive. And I imagine where there's no pressure, the climate must be just brutal.
Brutal is the right word. Mars has a truly severe climate. Its average surface temperature is about 40 Kelvin lower than Earth's average.
40 degrees colder on average.
But the defining characteristic is the extreme diurnal variation, the swing from day to night. Because there's no air to retain heat, the soil temperature just swings wildly. We're talking 60 to 80 Kelvin over a single Martian day.
That is an immense and rapid thermal shock every single day.
It is. However, there is one surprising data point. Near local Martian noon, thermal radiation studies, like those done by Sinton and Strong, they indicated that surface temperatures can actually reach a surprisingly high plus 28 degrees Celsius.
Plus 28 C.
Yeah.
That's genuinely warm. It's potentially above room temperature. Why isn't that a huge point in favor of habitability?
Because that is strictly the soil temperature. It's what's often called the radiative equilibrium temperature, and it's only under direct solar heating.
So there's no thermal inertia. It can't hold or transfer that heat.
Exactly. And here's the crucial caveat. The air temperature, even right near the surface, stays critically low. It's always below freezing. And that air temperature drops off rapidly, reaching minus 100 degrees Celsius by only 15 kilometers up, even at the equator.
So the surface itself warms up fast, almost like a piece of dark metal under a heat lamp in a vacuum. But the second the sun moves, or you stand just, a few inches off the ground, you are plunged right back into deep freeze territory.
Precisely. It's the difference between standing on blistering hot asphalt and being completely engulfed by sub-zero air. Now, this contrast does lead scientists to speculate about localized, more favorable microclimates.
What would create a microclimate like that?
The idea is that regions near past or maybe even present volcanic activity or deep depressions in the ground, they might be able to trap slightly warmer air and higher concentrations of water vapor.
Maybe from geothermal heating or some kind of gas venting.
That's the thought. In these localized little bubbles, conditions could, theoretically, be more favorable for life, if only for a little while, but we'd be talking about extremely isolated habitats.
From these tiny local microclimates, let's go global and look at the most visually dominant features of the Martian climate, the polar caps. Early on, what did scientists assume they were made of, and how did that understanding change?
Well, historically, most astronomers assumed the seasonal caps, the ones that grow so dramatically in the winter and shrink in the summer, were just big masses of water frost, frozen H2O.
Which makes sense. It's what we see on Earth.
It's the natural assumption. However, modern data, especially from infrared spectroscopy, confirmed a very different reality. The seasonal caps are primarily composed of dry ice.
Solid CO2.
Solid CO2. The atmosphere is literally condensing out. It's freezing onto the poles as winter arrives.
And that's why the pressure fluctuates a bit with the seasons.
It is. But that doesn't mean the water ice isn't there. It is still present. A smaller, persistent, bright spot of H2O ice remains year-round, hundreds of kilometers across, right in the center of those seasonal dry ice caps. That's the permanent polar cap.
Okay, so let's switch focus from the poles to the planet's sheer physical structure, the Martian topography. We know its gravity is lower, but what did the probes reveal about the scale of the landscape?
The altitude differences are just astonishing. We're talking up to 25 kilometers separating the highest points from the lowest points that have been mapped.
25 kilometers of difference.
This level of relief, what scientists call ruggedness, or the deviation from a perfect spheroid, is actually greater than what we see on Earth.
That seems kind of counterintuitive.
Yeah.
Why would Mars be more rugged than Earth, even though it's smaller?
Scientists attribute this enhanced ruggedness mostly to the planet's lower gravity. A lower gravitational force just permits geological structures, like mountains and canyons, to reach much greater heights and depths before their own mass causes them to collapse or flatten out.
And crucially, how does this extreme topography affect that already razor-thin atmosphere?
It means that the atmospheric pressure is highly variable. It's location-dependent.
So in the bottom of a deep canyon, the air is thicker.
Right. In deep depressions, the pressure can be nearly double the planet's average, maybe reaching 10 millimeter Hg. Conversely, in the high-altitude regions, like on top of those massive shield volcanoes, the pressure can be half the average.
And that pressure range is critical.
It's very critical because 10 millimeter Hg brings certain temperatures just a little bit closer to the triple point of water, which makes the possibility of transient liquid water slightly higher in the absolute deepest valleys.
So let's jump up high now, past the atmosphere we would inhabit, to the structure of the upper atmosphere. At these altitudes, we move away from molecules and more towards individual atoms. What did probes like Mars 3 and 5 and Mariner find up at 300 to 400 kilometers?
As you climb, the chemical composition just shifts dramatically, and it's due to a process scientists call photodissociation.
Okay, photodissociation, break that down for us.
It's pretty simple, really. It just means that the high-energy ultraviolet radiation and the X-rays that are streaming from the sun, which are usually blocked by a thicker atmosphere,
Like ours.
on Mars, they just slam into the CO2 molecules, and the energy literally rips the molecule apart.
So instead of CO2, what becomes the dominant component at 300 kilometers up?
At 300 kilometers, the main component becomes atomic oxygen, just oh whoa. The other product of that dissociation, carbon monoxide, CO, it tends to fall off more quickly with height because it's a bit heavier.
But you keep going up.
You keep going up to about 400 kilometers and above, and the dominant component of the Martian atmosphere shifts again, this time to atomic hydrogen.
Hydrogen at 400 kilometers, that's incredibly light. How dense is it at that height, and what does it form?
Well, at those altitudes, the densities are still around 10,000 hydrogen atoms per cubic centimeter, and this forms an incredibly vast, tenuous envelope of purely atomic hydrogen, which scientists call the hydrogen corona.
Corona.
Yes, and this corona extends outwards to enormous distances, maybe as far as 20,000 kilometers from the planet.
That sounds like a gigantic, almost invisible celestial cloud. How are the spacecraft even able to detect something so diffuse and so far away?
They used a very specific detection method, one focused on the Lyman alpha resonance line.
Okay, physics lesson.
It's a complex concept, but to simplify it, hydrogen atoms absorb and then they re-emit ultraviolet light from the sun at a very, very precise wavelength, 121.6 nanometers. This is the Lyman alpha line, and it acts like a unique spectral fingerprint for hydrogen.
So by looking for light that's scattered at exactly that specific wavelength, the probes could confirm this massive hydrogen cloud surrounds Mars, much like it surrounds Earth and Venus.
Exactly. But here is the critical dynamic connection. Because hydrogen is the lightest element and Mars's gravity is relatively weak, these hydrogen atoms are continuously escaping. They're dissipating into interplanetary space.
So it's a constant loss.
A constant loss, which means it requires a constant source of replenishment.
And that source connects right back to that tiny trace element we discussed earlier, the water vapor.
That's the powerful connection. The source of this renewal has to be the dissociation of the scant water vapor that's found in the deeper atmosphere. The sun's radiation breaks the water molecules, H2O, into hydrogen and oxygen. The hydrogen then rises up and escapes.
That's incredible.
What's remarkable is that the tiny quantity of H2O vapor present, that 1,000th of the CO2 content, is enough to maintain this colossal, continuous hydrogen loss. It tells us that even the minute amount of water Mars holds is dynamically cycling and constantly being lost to space.
We painted a pretty bleak picture of a cold, dry, hostile Mars today.
Yeah.
But search for life is fundamentally a search for past habitability, right? We need to trace that profound shift in our understanding of the Martian surface, which really starts with the dawn of robotic exploration in the 1960s.
Exactly. The new era began in 1962 with the deployment of the U.S. Mariner and the Soviet Mars probes.
And what was the first truly shocking revelation that was brought back by Mariner 4?
Mariner 4, which did a close flyby, it transmitted the first ever close-up photographs of the surface. And these images, taken from around 10,000 kilometers away, revealed a surface that was just dominated by a vast number of craters of all sizes.
So it looked like the moon.
It looked like the moon, and the appearance of a heavily cratered moon-like surface was a genuine, complete surprise to most of the astronomical world.
It just shattered that image of Mars as a dynamic, evolving world.
It really did. The received wisdom, the assumption, was that Mars was internally active, which would lead to fewer craters being preserved.
But someone predicted this, didn't they?
Interestingly, yes. Only one astronomer, the distinguished Estonian Ernst Öpik, who was working in Ireland at the time. He had predicted that Mars, because it lacks Earth's strong geological processes like plate tectonics to erase evidence, should be covered in ancient impact craters.
And his prediction was just ignored.
Largely ignored, yes. Only to be proved spectacularly right by Mariner 4.
It's a great lesson that sometimes the simplest, if maybe less exciting explanation is the correct one. Now, moving forward to 1971, Mariner 9 was designed to map the entire globe, but it ran into a temporary and probably very frustrating obstacle.
This is a wonderful anecdote that really illustrates the power of Martian weather. When Mariner 9 arrived in orbit, a massive, globally encompassing dust storm had erupted. It lasted for weeks, and it shrouded the entire planet in this impenetrable haze.
So they get there and they can't see a thing.
Not a thing. The mission organizers were forced to just wait, and they made these lighthearted jokes about spending hundreds of millions of dollars just to photograph a giant orange tennis ball.
Weeks of orbital waiting. That must have been excruciating for the scientists.
It was, but once the storm finally subsided, Mariner 9 performed these high-quality photographic surveys that covered the entire surface. It gave us the first comprehensive global map, and it was this mapping that revealed the truly colossal scale of Martian geology.
And one of the most stunning features, one that was barely visible from Earth, was revealed to be a true giant.
Yes, the feature that was previously known as Nix Olympica, or the Snows of Olympus.
The Snows of Olympus.
The Mariner 9 images show that this was not some modest feature, but the largest volcano in the entire solar system, a gargantuan cone about 500 kilometers in diameter and a staggering 20 kilometers high, topped by a huge caldera.
What's the primary significance of confirming past volcanic activity on such a massive scale?
Well, its size alone confirms a history of extremely intense volcanic activity, and this activity is the crucial factor linking geology to past habitability.
How so?
Volcanic outgassing, the release of gases like CO2, sulfur dioxide, and water vapor, is the only plausible mechanism to have ever boosted the Martian atmosphere to a pressure substantial enough to support liquid water.
And that leads us to the crucial evidence for past water, the dry riverbeds. I mean, the images from later missions like Mars Odyssey, they aren't just suggestive. They look exactly like river channels on Earth.
They absolutely do. The images clearly show these sinuous lines that bear a striking resemblance to terrestrial river channels. The key is the morphological detail.
What kind of detail?
We see what look exactly like tributaries feeding into larger main channels. And crucially, we observe a dendritic pattern, this branching structure, like the branches of a tree or a vascular system. That is the unmistakable signature of flowing liquid water eroding a landscape over very long periods of time.
So we can definitively rule out things like simple lava channels or, tectonic fault lines. They have different structures.
Entirely different structures. This had to be liquid flow. The presence of features that strongly resemble sedimentary deposits further reinforces the idea of sustained fluvial erosion.
But what does this all imply?
These features suggest that in past geological epochs, Mars possessed a much denser atmosphere and a much milder climate, a climate potentially suitable for Earth-like forms of life, dating back hundreds of millions or even billions of years.
So if volcanism was the engine that drove this change, what sort of environmental shift are we actually talking about?
Well, the hypothesis suggests that this warmer epoch was strongly linked to periods of very high volcanic activity. This activity would have released enormous concentrations of water vapor and CO2, boosting the atmospheric pressure tens of times greater than its current level.
Pushing it back up to that critical 20 or even 60 millimeter HG mark we talked about.
Exactly. That kind of pressure increase would have been high enough to allow significant, stable, open bodies of water to exist on the surface, which would support the formation of these immense riverbeds.
So Mars was once a hydrologically and geologically active world. The challenge then becomes, of course, why did it stop? And where did all that water and atmosphere go?
Before we had that definitive geological proof of past water, the biggest debate concerning Martian life centered on the observable surface changes you could see through telescopes.
Right. This was the long, intense debate over biology versus geology.
It was. Let's describe the surface as early astronomers saw it. Telescopic views revealed two main types of terrain: the reddish-gray vast deserts and the darker areas known as seas. And these dark areas had noticeable coloration, ranging from olive and greenish to sometimes even bluish tones.
And the key argument for life was that famous seasonal ways of darkening. How did this work, observationally?
It was very systematic and highly suggestive. As spring arrived in one hemisphere, the seasonal CO2 polar cap would start to shrink. And as it receded, a dark border, sometimes hundreds of kilometers wide, would appear at its edge.
Right.
This wave of darkening would then progress toward the lower latitudes, causing those dark seas to noticeably deepen in color and contrast. And the whole process would reverse in autumn.
So to an observer, seeing a wave of color sweeping from the pole to the equator in spring, it's very easy to imagine vegetation spreading as the conditions get better.
Many researchers did exactly that. Historically, they linked this color change to seasonal changes in Martian vegetation, something akin to plant life reacting to the perceived increase in humidity that was being released by the melting polar cap.
But the spectral analysis seemed to contradict Earth-like plants, right? Because they couldn't find the spectral fingerprint of chlorophyll.
That's correct. The spectrum of the dark regions did not show the characteristic chlorophyll absorption band. That's a spectral dip around 0.5 micrometers.
Which should have been a nail in the coffin for the vegetation idea.
It should have been. However, scientists who were enthusiasts for life argued that this absence wasn't conclusive. The famous proponent of this idea, G.A. Tikoff, argued that the severe environment, the intense cold, and the thin air would necessitate a different type of photosynthetic pigment.
How would that work?
Well, Tikoff suggested that if life existed there, it would have evolved a molecule structurally different from Earth's chlorophyll, maybe to absorb different, more available wavelengths of light, or to offer better protection against the harsh conditions.
Or even small changes could throw off the measurement.
He argued that even minor variations in the molecule's side branches were entirely possible and would be enough to dramatically change its spectral reflective properties, which meant the absence of the terrestrial dip was, in his view, inconclusive.
That is the essential caveat when you're looking for extraterrestrial life.
Yeah,
You might just be looking for the wrong chemical signature.
exactly. But the scientific community eventually developed some very compelling abiological counterarguments.
What were the geological and meteorological explanations?
There were two major lines of thought. One simple explanation was that the color changes were caused by changes in the color of salts that were contained in the Martian soil as the humidity increased.
A simple chemical change.
The salt just absorbs moisture from the melting dry ice cap, causing a subtle color shift, not biological at all.
And the second, more comprehensive hypothesis was McLaughlin's idea, which discounted life entirely.
Yes, the American astronomer McLaughlin proposed that the dark seas were deposits of volcanic ash, and their outlines were shaped by the predictable prevailing Martian winds. This was a powerful, purely geological framework.
And it could explain both long-term changes and the seasonal darkening.
That's right. For the seasonal wave of darkening, McLaughlin proposed a combined mechanism of wind and moisture. The dark basaltic ash is heavy, so the wind tends to sweep the lighter reddish-gray desert dust off of it.
Okay.
During the spring, as the polar cap retreats, it releases stored CO2 and some water vapor. This does two things. First, it potentially changes local wind patterns, which selectively clear away any light dust that settled during winter, revealing the darker ash underneath.
And second.
Second, the slight increase in humidity might chemically or physically alter the appearance of the ash deposits, changing their color or reflectivity just slightly, a shift toward darker tones, which then reverses in autumn as the moisture vanishes.
So the wave of darkening isn't a wave of growing life. It's a wave of wind-driven dust clearance, and maybe a slight moisture-induced chemical change in volcanic materials.
That's the key geological counterargument. However, this hypothesis ran into a little bit of trouble with one specific observational detail: the polarization evidence that was provided by the French astronomer Audouin Dollfus.
Why was polarization so problematic for the geological models?
Well, Dollfus observed that the polarization of reflected sunlight over the dark seas changes seasonally in a very characteristic way. And polarization analysis can tell you about the physical properties of the surface, specifically the size, shape, and structure of the particles scattering the light.
And crucially,
This seasonal polarization change does not occur over the reddish-gray desert regions.
so whatever is happening on the dark seas is a localized, seasonal, physical change in the particles themselves.
Exactly. The polarization measurement revealed that the particles on the dark seas were dynamically changing in size or structure in response to the seasonal shift, likely linked to the release of volatiles from the polar cap.
So how was that explained?
One camp suggested this implied huge, fast-reproducing colonies of microorganisms, a biological explanation, but the more probable answer remained geological.
Which was the physical absorption explanation.
Yes. The leading geological view posited that the surface of the seas is covered by fine, solid sand particles, maybe around 0.1 millimeter in diameter. And when atmospheric humidity increases, these particles physically change, either absorbing water or altering their crystalline structure. And this physical change modifies their light scattering and polarizing properties.
But it wasn't a perfect fit.
The difficulty was in fully reconciling these very fine-tuned polarization changes with McLaughlin's bulk volcanic ash hypothesis. So it kept the debate alive until the landers could provide a more decisive answer.
As fascinating as all the debates over color and geology were, they remained, indirect. Science required a direct search for the building blocks of life itself. And the first phase of this direct search focused on chemical signatures, specifically organic compounds, using infrared spectroscopy from Earth.
This brings us back to the famous, though later retracted, Sinton observation. Sinton initially reported the detection of absorption bands in the infrared spectrum of the dark seas bands in the region of 3.4 to 3.7 micrometers.
And why are those wavelengths so exciting?
Because those spectral bands are characteristic signatures of many simple organic compounds, molecules that contain carbon and hydrogen. If those were confirmed, it would suggest the foundational building blocks of life were present right there on Mars's surface.
But the finding was later discredited.
It was found to be erroneous, yes. But the scientific caveat here is still important. Even if organic molecules had been confirmed, they don't automatically equal life. Complex organic molecules could have formed during Mars's primordial atmosphere. If life never arose, and if the environment lacked sufficient oxygen to drive oxidation, those molecules could have just remained preserved or conserved in the soil for billions of years.
But preservation is the key challenge because of that extreme physical barrier we noted earlier, the lack of a protective layer.
That is the critical environmental constraint. The absence of free oxygen means there's no protective ozone layer. So solar ultraviolet, UV, radiation is completely unimpeded, and it hits the surface directly with destructive force. The Martian atmosphere is far more transparent to these destructive rays than Earth's is.
So any complex organic molecule, the very foundation of life, that was exposed on the surface would be rapidly photodissociated or just broken down by that constant UV barrage.
Precisely. And that fact alone makes the possibility of complex organic molecules, let alone living organisms, surviving and thriving on the immediate surface highly problematic. And this high-stakes context is what framed the most ambitious missions of the era.
Which leads us to the centerpiece of the early search, the Viking missions of 1976. This was the first time humanity had the chance to perform direct biological and chemical analysis on another planet. What was Viking 1 and 2 explicitly designed to do?
The Viking landers carried extremely sophisticated, highly publicized instruments that were designed to perform multiple chemical and biological analyses on Martian soil. The explicit goal was to find reliable signs of microorganisms by testing for known life processes. Specifically photosynthesis, which they called CO2 assimilation, metabolism, and respiration.
And the results were far from clear-cut. They led to years of confusion. Let's discuss the ambiguity of those initial metabolic results.
The initial results were indeed famously described as somewhat uncertain. One experiment, the labeled release, or LR experiment, which looked for metabolic activity, showed a positive result.
A positive result?
Yes. When soil was exposed to a nutrient solution that contained radioactive carbon, a burst of radioactive gas was detected. This looked at first just like respiration, a sign of active metabolism.
That's the false positive that generated so much excitement and so much confusion. Why did scientists ultimately dismiss this as a sign of life?
Because the control experiments really complicated the picture. When scientists performed the same tests on samples that had been sterilized by heating the soil to high temperatures, which is a standard technique to kill microorganisms, they still observed some similar reactions, just reduced.
So something non-biological was happening.
It led to the conclusion that the surface soil was not biologically active, but rather chemically highly reactive. Subsequent research pointed to the presence of perchlorates, these highly reactive oxidizing salts, which could spontaneously release gas when you mix them with the LR nutrient solution, mimicking biological metabolism without the need for actual life.
So the metabolic tests were inconclusive, but they leaned towards reactive chemistry. But the final critical blow came from the definitive chemical analysis.
That's right. The most discouraging and ultimately decisive result came from the chromatographic analysis. Gas chromatograph mass spectrometers were flown specifically to separate and identify individual organic molecules in the soil. The instrument was designed to find the products of microbial life, like complex carbon chains.
And what was the finding?
They found no traces whatsoever of complex organic compounds in the Martian soil samples they analyzed at the 2 landing sites.
Nothing at all.
The results were essentially absolute zero for organics.
And that lack of finding was just devastating, especially when you compare it to the control test back on Earth.
It was damning. The same exact instrument, when they tested it with soil samples from Antarctica, a place known to be extremely cold, harsh, and sparsely populated, but still containing fossil and current organic compounds, found significant quantities of those compounds.
So the instrument worked.
The instrument worked perfectly. The lack of any organic traces in the sampled Martian soil, when the instrument was proven capable of detecting them in comparable environments, led the scientific community to the strong conclusion that contemporary surface life was highly improbable.
But the argument that Vikings simply landed in the wrong spots, it still persists, especially from life enthusiasts. How does the scientific community weigh that argument against the evidence?
It's a valid argument, but it's one that's constrained by environmental reality and, frankly, economics. Enthusiasts correctly argue that life could exist elsewhere, perhaps miles beneath the surface or in those little localized microclimates.
But the surface is a tough sell.
We have to consider the universal constraints. If UV radiation is universally destructive on the surface, the likelihood of finding widespread surface life diminishes, really regardless of the exact landing site.
And then there's the economic cost of trying to validate that.
Yeah, exactly. Each Viking mission cost hundreds of millions of dollars at the time, a prohibitive cost for a wide-ranging, exhaustive search. So while the ultimate answer absolutely requires more direct experimentation, the totality of the facts.
The UV, the pressure.
The inescapable UV radiation, the near vacuum pressure, the frigid cold, and the empirical lack of organics in the sampled soil, it all pushes the scientific consensus towards skepticism regarding the current widespread existence of living organisms on the Martian surface.
So what does this all mean? We've completed our deep dive through decades of discovery. The evidence is, I think, pretty clear. Mars today is defined by its hostility. It was cold, dry, bathed in destructive UV, and wrapped in a pressure so thin that liquid water is generally impossible.
But that harsh present is offset by a truly compelling past. The vast dendritic networks of dry riverbeds alongside the confirmed scale of volcanic activity are powerful testaments to a former epoch. Mars once had a denser atmosphere, potentially stable bodies of water, and a climate mild enough for the genesis of life.
Yet, when we moved from remote sensing to direct contact with Viking, the initial ambiguity was resolved by the hard chemical data. The failure to find any organic compounds pushed the scientific perspective heavily towards skepticism regarding the prevalence of contemporary life on the Martian surface.
We've established that complex life can adapt to severe cold. I mean, humans managed to survive in minus 82 degrees Celsius in Antarctica, for example. The temperature alone doesn't necessarily rule out microbial survival, though it certainly makes it challenging. But I want to leave you with the ultimate physical constraint to consider.
What's the biggest non-negotiable factor beyond the UV radiation?
It's the pressure. Given the immense possibilities for organisms to adapt, the current near-vacuum state where water sublimates instantly raises a critical question about the genesis of life. Could life have ever arisen in an environment with such low pressure? Or does the necessary chemical scaffolding for life to start, the required solvent function of water demand, the necessity of a sustained, thick atmosphere for that initial biological leap to occur?
A question that suggests the window for life on Mars was not just finite, but perhaps extremely narrow, limited to that brief, ancient period when its volcanoes were still vigorous enough to hold the air in. Thank you for joining us on this deep dive into the cold, dry search for Martian life.